All right, so now that we know what functions are, let's talk about what domain and range are, and specifically how they relate to the idea of a function. What do I use them for? Where do they come from? All that good stuff. Okay, so knowing domain and range of a function is how we know which numbers we're allowed to put into a function, as well as which values we should expect to get out. So your domain is all possible inputs. And typically the easiest way to express this is your using interval notation. Interval notation. Okay. Same for range. We like to look at interval notation. So the Cartesian plane, the coordinate plane that you're looking at, you're used to looking at, is actually two different number lines. You have a number line that we call x. When we talk about domain, we're just talking about where on that number line is that function going to exist. And when we talk about range, now we're talking about the vertical number line, which we call y. Where on that number line is this function going to go? Okay. For discrete data, which means I just have a list of data, this is just a listed set of those data points. For continuous data, we use interval notation. Now, typically speaking, domain and range is the shortest method to give us the most information, which is why we spend the time to look at interval notation and understand it so that we can get there. This is just a review of interval notation, okay, on the top up here. And remember that we never include the variable itself. To determine domain, we need to identify the input values and any restrictions that might be on those. Okay, now in rational functions, something like 3 over x minus 5, our restrictions, remember we went through these when we were solving and we said we had restricted values. Well, those restricted values translate directly to the domain. I know that x minus 5 cannot be 0, and I can use that information to look at my domain and say, well, if you put in this number, you're going to get a problem, right? For radical functions, which we have also looked at very briefly, we'll come back to them in more detail. So for radical functions, things like f of x is 3x minus 2. For that type of function, well, when we know if we're going to graph, we have to avoid imaginary numbers. So the thing inside has to be greater than or equal to 0, or I'm going to get an imaginary number. Okay, and that's what we mean by what type of numbers could cause problems if I plug them in. And then once we have kind of this scenario, then we write our domain as an interval. Okay, so domain and range for each of the following. These first two are discrete data. I just have a list of points, and so my domain for the first one is going to be a list of the x values. So 2, 3, 4, 5, and 6. The range is going to be the list of the y values. 10, 10, which I don't have to list again, you just list it once. 10, 21, 32, and 43. For the next one, my domain would be -5, 0, 5, 10, and 15. My range would be 4, 0, -4, -8, and -12. We do, -8, -12. We do usually prefer them to be from smallest to largest, so we would normally start that with -12 and then work our way back up to +4. It's fine. I'm not going to take off points for that. especially in this scenario, in this context, because we're just kind of like figuring out what all of this is, okay? Now, for the rest of these, you are going to want to use Desmos if you're not 100% sure how to do them algebraically, or if you need some sort of visual to help you do this, okay? Now, f of x equals x squared minus 1 looks like it's got a point at 0, -1, and then it grows in both directions forever. So if I look at just horizontally, okay, so just at the domain, it's going to hit every x value eventually. Okay, maybe not quickly, maybe not the way I want it to, but it is going to hit every x value eventually. And so my domain is going to be all real numbers, but I need to write that in interval form. So my domain is from -infinity to +infinity. Now the range, now we're looking at it vertically speaking. So starting down here and working our way up. What part of that graph is going to hit that, or what part of that number line is that graph going to cover? Well, it doesn't actually hit anything down here, right? It's not there. And so this is greater than -1, right? We're starting at the bottom and we're working our way up. As we work up this number line, the first place that we see a graph, or we see part of that value, then that's where we start our function. So we're going greater than -1. So I'm going from -1, and as I keep going up, this graph is going to keep following me up. So it's going to go to +infinity. Now there's a closed dot at -1, which is why I have a square bracket there. Okay, so -1 to infinity. Let me erase this. All right, so let's look at f of x is -2x squared plus 3. You can go to Desmos, you can graph this. It's going to look something like this, okay, where this is the point 0, 3. So if you look at this algebraically, quadratics, the domain for quadratics is always all real numbers. There's nothing that I plug in there that's going to cause any sort of problems or any sort of issues. So if I have a quadratic, it's all real numbers. Okay, no thought, no thinking, no algebra, no effort. Just if you see a quadratic, everything's game. Okay, now for range, you're going to want to look at the graph. Okay, so if I'm starting way down here and I'm working my way back up, because I have to go from smallest to largest. At the very, very bottom of that graph is -infinity. And as I walk up that axis, eventually the graph stops. And the graph happens to stop at +3 with a closed dot. So that means that my graph, or my range, goes from -infinity to +3. All right, f of x is 5 minus 3x minus x cubed. And if I remember correctly, it's going to look, let's see, -x cubed, so it's going to look something like this. Okay, x cubed, large polynomial. So again, my domain is everything. Okay, that graph is going to continue up and down for infinity. I'm set up, good to go. Okay, I'm sorry, it's going to continue left and right for infinity. I'm thinking of range. Then I go to range. And if I look at this graph and I start way down here at the bottom and start moving this direction, I can always see part of that graph. It's always there. And since it's always there, my range is also negative infinity to infinity. So I don't have to run into an error. There's nothing there that's going to cause me any problems. It's just is what it is. Okay, let's erase. All right, so look at the next one. If I take f of x is the square root of 2x plus 5. And when you graph this one, it's going to look something like, this is going to be negative 2.5, and then it's going to go this direction. Okay. So now, from the shape of the graph, I can kind of see I'm going to have issues with this graph in both directions. If I look at it from the domain perspective, okay, so starting way back over here and moving this direction, the first time that I hit something right there on from the left side, coming from the left, working right, first time I hit the graph is at negative 2.5 or negative 5/2, however you want to write it. And then as I continue moving to the right, the graph continues with me, and it will continue with me on until infinity. And so now that I've got that, all right, cool, I can go and talk about range. Now the range of this graph is vertical. So if I start way down here and work my way upwards, the first time that I come across that graph is at 0. So my range is going to go from 0 to positive infinity, because it's going to continue to grow along with me as those numbers get bigger. Okay. All right, domain and range gets a little bit trickier when you start to look into different types of functions. So x squared plus y squared equals 25. This is actually a circle, and I don't know if Desmos will graph it for you 100%, so I'm going to graph it. 25, we take the square root of this, so that's going to be a 5, and that means that its radius is going to be 5 all the way around. Okay, so I've got a circle. It's got a radius of 5. I know it's beautifully drawn. So I look at my domain and range. So the domain of this circle on the x-axis, when I start from left to right, I start seeing the circle at negative 5, but when I pass positive 5, I stop seeing the circle. So my domain just goes from negative 5 to positive 5. Similarly, the range, as I start from the bottom and work my way up, I start seeing a circle at negative 5. I stop seeing the circle at positive 5. So the domain and the range happen to match. That's not always the case, but in this case they do. So they happen to match, and they happen to be from negative 5 to 5. If I take f of x equals x plus 2 over 1 minus x. Now the graph of this one is going to look really weird. And I would just do this one in Desmos if I was you. That's totally fine. You're going to get an asymptote at negative 1 and a vertical asymptote at 1. So this graph, I think, looks like this. It might swerve the other way. So I've got this graph. And here, instead of having values that I can see, it's actually easier to point out places where I can't go, right? If I take 1 minus x, and it can't be 0, then 1 cannot be x. And so that means for my domain, I can be anywhere except positive 1. And in interval notation, that means you can start at negative infinity, you can go to positive 1, but then you have to step over positive 1 before you continue on. If I look at the range, now there's a point at negative 1, and on Desmos, you're just going to have to inspect it and look at where it doesn't go. We'll show you how to find these when we get to rational functions, but it's not really worth it right now. Right now you can use Desmos. So my range, for the range, I can't go at -1. So I'm going to go from -infinity to -1, and then -1 to +infinity. So what we're saying is you can go anywhere except that number. All right, so if we look at the next one and kind of identify what's going on here. We have a similar scenario. We have f of x is 2x minus 5 over 2x minus 3. You can graph it. You're going to get a vertical asymptote at +3/2. You're going to get a horizontal asymptote at +1. Okay, so this is an x asymptote, this is a y asymptote. So when you graph that, it's going to look kind of funny. It's going to work around those two places. So I'm saying x cannot be 3/2, y cannot be 1. So domain. Domain deals with the x values. So I can go everywhere except +3/2. So -infinity to 3/2, 3/2 to infinity. For the range, I can go anywhere except +1. So I'm going to go -infinity to +1, and then +1 to infinity. Okay. Anywhere except those numbers. All right, the next one, f of x, is the cube root of 4x minus 16. If the index is odd, if there is an odd index, then there are no restrictions. I don't have to worry about it. Negative numbers can exist if I have an odd index. So my domain is going to be all real numbers, -infinity to +infinity, and my range is also going to be all real numbers, so -infinity to +infinity. Okay, an odd index has no restrictions. Now, if the index is even, so f of x is the 4th root of x squared plus 2. In an even index, then our argument, I'll call it an argument, argument must be positive, greater than or equal to 0. So I'm going to take what's inside, so x squared plus 2, I'm going to set it greater than or equal to 0. So x squared must be greater than or equal to -2, so x has to be greater than or equal to plus or minus I rad 2. Now if you get an imaginary number here, that means this is always true. I don't have to worry about it. Okay, so then you're just going to go and graph, put it in Desmos, graph it, see what your graph looks like, plot your, or decide on your domain and range, and go from there. Okay, so, but if it were something that came out to a different type of problem, then I have to worry about, okay, is it greater than or less than, is it this or that, and then decipher it. But again, at this stage, you can use Desmos, graph it, read it, put it in interval notation. Okay. Set builder notation, we talked about set builder notation. So this is more or less just a review. So changing between them, if I have the domain of a function set from 5 to 10, I can change that to inequality notations, which is what you probably used most of high school, and just say, well, this is all the values of x that are between 5 and +10, including 10, but not including 5. And then if I want to change that to set builder notation, we just add these brackets on the outside. We put this vertical bar and the x, and then you take exactly that notation and put it on the other side of that vertical bar. And that is considered set builder notation. Okay, so it has uses. They want you to practice it. You're going to see it again in statistics. Probably not as often, but you'll see it in statistics more than you'll see it here. So they just want you to practice it a little bit. Okay. Now the last thing in 3.2 is a thing called piecewise functions. Now piecewise functions, I like to call them Frankenstein functions. I used to teach them in high school in October because it's a fun Halloween lesson because you can talk about Frankenstein and, you know, cutting up pieces and whatever. And so you get this idea of, I have this really complicated rules, and depending on which x value you give me, there's a different rule for you to have to follow. Okay, so what we do when we graph these, I'm going to graph this part in blue. I'll use a different color for each piece. So I'm going to graph x plus 2. It's going to go through 2. It's going to have a positive slope of -1, or a slope of +1 going in either direction. Except that this says for x is less than 0. Okay, that means that any value greater than x is 0, I have to erase it. And since it's not equal to 0, we put an open dot there. Okay. Then I'm going to graph 2/3 x for between 0 and 6. So here's my function. It goes through 0, 0. It goes up to right 3, up to right 3, up to right 3. So I've got this function. Okay. And then we're going to look at our restrictions. Now our restrictions say from 0 to 6, but notice how neither one of them includes 0 or 6. So I need to erase this side, and anything bigger than 6, and instead I'd have to go back and on those two endpoints put an open dot. And I did mess up my blue graph, so I'll just, sketch that back in. All right, and then the last piece is -x plus 6, but only where x is greater than 6. So -x plus 6 is going to cross at +6. It has a slope of -1, and I'm just going to skip there for a second so that I don't mess up that line. Okay. And it would continue on up in this direction. But I only want it where I'm greater than or equal to 6. So if it's less than 6, we don't want it. And because it's equal to 6, we put a closed dot there. Okay. Now the part here that gets a little bit more confusing is domain and range. Okay. The domain of this function, I have to look and use my vertical line test. Okay, so I put a vertical line here, and actually that place is fine because both of these are open dots. And since they're both open dots, I have to say x isn't 0. I don't have any way to evaluate 0. They're both open dots. And then I go to the next place where it might give me some issues, and I put my vertical line. And since this one is open and this one is closed, I can include that point. If they're both closed, it's not a function. So they shouldn't both be closed. You could have both of them open or one open and one closed, but you shouldn't get into a scenario where you have both of them closed. So for my domain, all I have is that x cannot be 0. So that's going to be -infinity to 0 and 0 to infinity. For my range, I have to now, I don't really care if it's 1 to 1. I just want to know, is there anything that it's not going to be? Okay, so right here, that's fine. My highest value is going to be that +4, but notice that it's an open dot right there. And it goes down forever, goes down forever. So my range is going to be -infinity to +4, but not including the +4. Okay, so domain and range can get a little weird with those, but basically you're kind of looking for what's the smallest one, what's the biggest one, and do they have any places that they can't go? Okay. All right, so that's it for 3.2.